Well, welcome to our show. I'm Doug Bundy. Nothing's working right. I don't know what the big deal is. It wouldn't start. I had to reboot the thing, so we're a few minutes late. And then I tried to play the little intro I've made, but that didn't show either. But anyway, welcome to our show. For what it's worth, we're here as the Honest Investigators Talk Shop show. I'm your host, Doug Bundy, president of the Larson Research Center, where we are unveiling the universe of motion. Today is Saturday, January 9th, 2016. I announced in our inaugural show last week that I'm presenting the lecture that I promised to present 9 years ago at the end of lecture 2, entitled On the Coming Revolution of Fundamental Physics. The videos of both lecture 1 and lecture 2 that I presented back then are available now on our YouTube channel, the LRC Physics channel, as well as on our website at lrcphysics.com. We encourage you to go there or watch and subscribe and like and all that stuff. We're also on Facebook, the LRC Physics page or group, actually, I guess it is. But anyway, there you can make comments and we can talk about these lectures. I also explained last week how that we here at the Larson Research Center, or the LRC, refer to Newtonian-based program of the mainstream physics, of theoretical physics, as we refer to that as the legacy system of theory, or the LST, and the vector-based mathematics that it employs is referred to as the legacy system of mathematics, or the LSM. This not only helps us distinguish between our system of theoretical physics, known as the reciprocal system of physical theory, and our scalar-based system of mathematics, known as the reciprocal system of mathematics, but of course it also makes it much easier to refer to them. So in this part 1 of our series, entitled today Scalar Mathematics for Scalar Motion and Scalar Motion for Scalar Physics, we begin the journey of unifying the LRC's RST-based scalar motion theory of physics with its RSM-based scalar number formulation of mathematics. Now, in order to do this kind of a presentation, I need to be able to do a lot more with the buttons and stuff here, and so you'll have to bear with me. Hopefully I'll be able to make it work. But what I want to start with is a presentation. Aha, it came up. That is in PowerPoint, and so then I'll use that and I'll be able to mark on it and so on, I hope. I need to do a few things here with this to get it to work right. There, okay, so I'm not completely out of the picture. I'll put it right there, maybe a little less so it won't totally interfere with some of the slides. And then I think what I'll do is turn off the lower third as well, and that way that won't cover up the bottom part of the slide there. Okay, so this is like a whiteboard we've got here, and this is entitled again, well, it has to do, this whole series of lectures has to do with a multidimensional scalar number system, which is kind of a oxymoron for normal physicists and mathematicians. Scalars normally aren't thought of being anything but zero-dimensional. But here we see that the scalar mathematics for scalar motion And scalar motion for scalar physics is our program. We've got to have that in order to, as we'll see at the end of this presentation, we wouldn't be able to do it without it. It's just a totally different approach to physics than the mainstream or the normal, or what we call the LST, the legacy system of theory. But without going into the details, I should point out that the LRC's scalar motion theory of physics differs from Larson's own theory fundamentally, although it's based on his new system of theory that we call the RST, the Reciprocal System of Physical Theory. The difference lies in the understanding of multidimensional scalar motion. It was Larson's conclusion that scalar motion includes rotation, and he based his theory from that point on rotation. However, we differ. It's our conclusion that scalar motion is restricted to a change of scale or size only by definition. A rotation of a scalar vibration, as Larson conceived of it, is just incommensurate with scalar motion as we define it. For much more information on this, you can go to our website, lrcphysics.com. But as a result, the LRC's theory does not rotate lower dimensional scalar motions and then build these into higher dimensional combinations, as does Larson's theory. But rather, it begins with fundamental three-dimensional scalar motions and then builds these entities into combinations of scalar motion, as we will see shortly. Recall that the first fundamental postulate of the RST states that the physical universe is composed entirely, as you can read here on this first chart. I hope it comes out very well enough to read it. But the physical universe is composed entirely of one component, motion, existing in 3 dimensions in discrete units and with 2 reciprocal aspects, space and time. So when we see this, we see that there's 2 fundamental postulates. We'll get to the second one later, but this first one was really quite, I guess you'd call, real restrictive. You know, it really states what the universe consists of, and we have to then deduce what that means, the implications of this postulate. So without going into a whole lot of detail on it, given this 3D motion or uniform expansion of space and time that it calls for in 3 dimensions, we get a perfect nothingness thereby in this definition. And for anything, there has to be for anything to exist, there has to be a deviation from this perfect uniformity. And Larson concluded, and we agree, that the only possible deviation from this one-to-one progression of space and time is a reversal in one or the other of the 2 progressing aspects of the motion. This is a contentious point, however, for many, because they look for a mechanism to cause the reversal. But Larson's answer was really philosophical. Anything that can happen will happen, was his answer. This is easier to understand when we represent the uniform progression mathematically, and that's then why we're presently pursuing that end. In the equation of motion, V equals ds, or delta s, over delta t, the unit velocity is a change of 1 unit of space per 1 unit of time, as can be seen right here on our chart. And then that's I wrote here delta 1 is a change of 1 unit of space over 1 unit of time. If the change, if the change in the numerator and the denominator on this 1-for-1 basis is ever increasing, then the only way that a deviation from unity can occur is a continuous reversal from increasing to decreasing to take place in one of the two reciprocal aspects of the motion. Larson was seriously taken by this insight, since he knew from observation that a continuous oscillation is just as permanent a motion as a continuous uniform motion. It's something that we can observe in nature and therefore deduce that its existence in the theory is justified. Hence, two deviations from uniform motion are possible. One, when the space aspect of the uniform motion oscillates at some point, and the other when its time aspect may happen to. In terms of numbers, these two possibilities are easily represented by two reciprocal ratios where S equals S over T is equal to 1 over 2, and also then 2 over 1 in the reciprocal case, because it takes one cycle of space oscillation over 1 unit of space it takes 2 units of time. See here, this is only in this form, you'd have to think of this as one cycle. Actually, it's one half of a cycle, but we'll look at that later. Think of this as one cycle taking 2 units of time, just as swinging pendulum. You can think of going one way in one cycle of time and then going the opposite way in the next cycle of time. And then the unusual thing is, is the reciprocal of that is where time is the cycling here, oscillating, and space is it's taking 2 cycles of space to do that. So so what we'll say then is, since one cycle of space oscillation over 1 unit of space takes 2 units of time, and one cycle of a time oscillation over 1 unit of time, over 1 unit of space, takes 2 units of space. So that might be an unusual thing to think of in terms of space reversing and oscillating. That's easy to see, but time doing the same thing but giving us a completely different velocity might be very might cause a lot of people to perk up and arch their eyebrows and what are you talking about here? But bear with us, we're going to see. In Larsons theory, the oscillations were back and forth over 1 unit of 1 dimension, but here in the LRC's theoretical development, the oscillations are volumetric pulsations, if you will, or 3D oscillations, one of space and one of time. These oscillations cannot be represented by the wave equation, of course, which depends on the imaginary square root of -1 to mathematically formulate rotation in 1 dimension. That is, it depends on the square root of -1 to calculate the position of a point on the circumference of the unit circle. When physicists, mathematicians figured out how to do this, it now is looked out upon, as we'll see here in a second in a video we're going to play, as one of the most major and significant accomplishments in the history of physics. So let's watch this video where it demonstrates this fundamental formulation of rotational motion, where as the sine and cosine of the angle changes, the intersection of the hypotenuse line of the right triangle defined on a fixed coordinate system with the circumference of the unit circle moves along quite nicely, as long as one of the numbers is the imaginary square root of -1, designated with the letter I. Now, Neil Turek, he's the head of the Perimeter Institute, explains this in the video.
Now I want to introduce a more bizarre mathematical character. And it took people 2,000 years to make the next great leap in mathematics. Okay, geometry was pretty important. With Pythagoras' theorem, you could build pyramids and structures, and architects wouldn't make a living without Pythagoras' theorem. But it took 2,000 years before the next huge leap forward in mathematics, and that came about with this strange character I. So the problem was that the problem arose in solving equations. Mathematicians like to solve equations. That's what they do. So you write down x squared plus 3x plus 2 equals 0, or x to the 5th plus x to the 4th. So they were busy in the 16th century solving these equations. In fact, they had competitions to solve equations. And so nobles would set equations, and then people would arrive, and they would work desperately for a couple of days, and the one who solved the equation would win the prize. So there was a guy who, at the time, who discovered that if he imagined a number whose square was -1, then he could actually solve lots of equations. And he kept the trick secret. It wasn't published for 20 or 30 years. And then finally word got out. And this number I, the imaginary number, came into being. So it's a very strange thing. It sounds very counterintuitive. How can I have a number whose square is negative? We all learned in high school that a number times itself. Two negative numbers, a negative number times itself will give a positive number. So it's obviously not a negative number. It's not a real number at all. It's an imaginary number. Actually, in my inaugural lecture in Cambridge, I introduced this number, and I didn't really explain it. And my brother is an economist who happened to be at the lecture, and I talked about imaginary things. And he said to me at the end of the lecture, if you allow yourself imaginary things, I'm not surprised you can do anything. But this imaginary number is very, very, very precise. There's no ambiguity about it. It's not a fiction as far as mathematicians are concerned. It's the real deal, this I. Now, why? Because as soon as you've introduced it, you can solve all equations. Okay, so it's rather easy to show. I won't show it in detail, but it's rather easy to show using the concepts I will describe that any possible equation has a solution. Furthermore, any equation which, say I wrote down x to the 23 plus some number times x to the 22 and so on equals 0, there will be 23 solutions of that equation. And that's rather easy to see. If somebody wants to ask a question afterwards, be happy to answer it. It's called a fundamental theorem of algebra. So all of a sudden, with this one extra character in the game, a problem that had seemed impossibly complicated and difficult, because some equations seemed to have solutions, some didn't have solutions. Now all equations were on the same footing, and they all had solutions. It's an incredibly powerful, simple idea. Once people had, now it relates to Pythagoras' theorem as follows. Once you have the idea that you have this guy I, and this is a very valuable idea. It's not an iPhone or an iPad. It really annoys me when that was branded as I, because this is the I. Okay, I'm sorry. This I will be here for eternity. I'm not sure about the other one. Okay, so we take the I. Now, we are going to enlarge our space of numbers. We have a number x, which could be any number from -infinity to infinity, an ordinary number. And then we have another kind of number, which is a multiple of I. So, and we put the two things together. We say, I'm going to allow numbers which have a real part, the x part, and the imaginary part, which is the multiple of I. Okay, so the dimension, suddenly I've gone to numbers not being on a line. They're now in 2 dimensions. I can go along the line. I can also go in the I direction. And so I can go along x and up in y, and I get this number, x plus iy. Now, one of the most basic and important functions in mathematics is the exponential function. We all know about exponentials because of inflation in prices. That's a bad thing. If prices rise by 10% per year, the prices are going to go through the roof. And they will follow exactly this law. If the x is 0.1 to represent the 10% growth per year, it will grow as e to the 0.1, where e is a number invented by Euler. Euler, most brilliant mathematician in the world in the 18th century. So we know about exponential growth. It applies to a huge number of things. So if you have bacteria multiplying, each bacterium doubles every 20 minutes, then the population of bacteria will grow exponentially. Compound interest, many things follow this law. In terms of mathematics, this is the simplest solution to one of the simplest equations, which is that the derivative of a function, meaning the slope, is equal to the function. So it's telling you that how much the function will change as you increase go along in x. The change in the function is proportional to the function. Solution of that equation is this exponential function. Okay, so it's a very basic function in mathematics. Now, it's not very good for modeling the real world. Sometimes it's good, because sometimes really things do go crazy, okay? But a lot of what happens in the world is rather regular. I mean, things don't just keep growing forever. So Euler, who invented this kind of mathematics, differential equations and these functions, decided, what happens if I exponentiate? You see, this is exponentiating a real number. So he said, what happens if I exponentiate this imaginary number? Okay, very natural question. Does it also go through the roof? Well, no. When you exponentiate the imaginary number, it goes round in a circle. Okay, so the exponential of an imaginary number times theta, where theta is a real number, it's an angle, actually. It's an angle here. It gives you the trigonometric functions, cosines and sines. And if you remember your geometry, the cosine is this side divided by that, and the sine is this side divided by that. And I've taken out the scale. I've just set the hypotenuse to be 1. So you see the fact that the exponential of an imaginary number gives you a point on a circle. And so as theta runs, this angle theta can grow, the point is just going to go running around a circle. Now that's like a lot of natural phenomena. So if something in nature goes back and forth, it's going to be described by mathematics like this. Whereas if it goes one way and explodes, it will be real numbers. Okay, so that's what Euler discovered. This formula here connects differential equations, which give you exponentials, to algebra, which gives you I, to geometry, which gives you these. Okay, it's been called the most amazing formula in mathematics. So I hope you're beginning to be a little bit impressed with I. Okay, there's a lot of good stuff for you at very little expense. So let's see it in action. So here we are. We have this circle, and the angle is the angle subtended by this pointer. And as the theta changes, this e to the I theta is running around. And you can see its real part is going backwards and forwards and backwards and forwards. And so if I use that real part to model a wave, which is also traveling upwards, as its amplitude is going back and forth, I get what we call a sinusoidal wave. So the wave is now following this function, which came out of trigonometry, through this construction. And it turns out this is how nature works. Basically, everything that goes back and forth in nature can be described in terms of functions which look like this. In particular, when Maxwell discovered the equations of electricity and magnetism, the astonishing discovery he made as a consequence of figuring out the right equations was that he could describe light. And here it is. Here's a light wave. The yellow arrows are the electric field. The blue arrows are the magnetic field. The pattern, this field pattern, moves along in space at the speed of light. And Maxwell showed the known laws of electricity and magnetism gave rise to light, and they predicted its speed, and it was correct within a few percent. So that I call the greatest discovery in physics of all time. To get out of some completely different phenomena, electrical forces and magnetic forces, and figure out all the right equations, and lo and behold, you predict light. See, it's not just one thing you predict an infinite number of things. Because it happens that the equations Maxwell found don't tell you the scale of the light, because those equations have no scale. So you can take a light wave and shrink it down to a very short wavelength thing, like an X-ray or a gamma ray, or you can stretch it up to huge radio wave, which is kilometers long. The undulations are kilometers long. And they're identical. As far as the equations go, they're all the same thing. Maxwell's equations have no scale, and that means they can be applied across all scales. So out of one equation, you've predicted an infinite number of phenomena. And of course, people didn't even realize there were radio waves before Maxwell's equations. These were realized as a consequence of the equations. They knew about light, okay, and when they knew there was an explanation for light, the natural thing to say was maybe there's some other waves. And that's how radio waves were discovered, and that's why people started to try to make radio waves and communicate with radio waves, and so on. So this is, again, one of those simple ideas that turn out to have incredible impact and universality. In fact, it would be fair to say that in physics, everything is a wave.
Everything is a wave. Well, obviously, the idea of multidimensional scalar motion and corresponding multidimensional scalar numbers is going to be iconoclastic to this established way of thinking in a huge way, if it ever makes any sense. Everything is a wave, they say, but it may appear that way, but it's possibly a good or probably a good idea to define a wave if you're going to say that everything is a wave. And for instance, that one-dimensional wave may not be the only kind of wave. Is there a three-dimensional pulsation as a wave, the kind of thing that we're looking into? If so, how can we formulate the expansion contraction oscillation in 3 dimensions in a manner analogous to rotation in 2 dimensions? It's really, one is one-dimensional, the other is 3-dimensional. One is a moving point, the other is a changing size. So it doesn't seem like there's any way to connect the two systems. Unlike the sine wave oscillation of the real axis in the video we just watched, with the changing magnitude over time from +1 to -1 and back, describing the wave over time, the magnitudes along the X, Y, and Z axis in the oscillating ball increase and decrease simultaneously. Moreover, because these 3 magnitudes are scalar, they increase or decrease in 2 opposite directions, quote, directions, from the origin in the middle there. And they do this in each dimension simultaneously, as we're going to see now in this next slide. Here, and I hope you can see that. You might not be able to read it, but here we have the axis of time going up just like he did in the video. But at time 1, here we see an expansion from the center, which is the red dot, out in both directions. This is a one-dimensional expansion, so that the left side there would go to the magnitude -1, and the right side to +1 at the same time. So they spread out, you see, expanding out from the middle. Then at time 2, we have 2 units on the left and 2 units on the right for a total of 4 units. And then 6 units when we've got 3 and 3 at T3, and then at T4 we've got 4 and 4, and so on. So this is quite a different motion. This is what we would call a one-dimensional expansion of space. And we've got 1 unit increments in each of the 2 directions there, as you can see. So if it's space, then because in our postulates there's no difference between the properties of space and the property of time. They're just reciprocal of one another. So the properties of one are the properties of the other. Now, what I'm trying to show here in these corners, you see a one-dimensional expansion shown here, and it's the same thing as shown up here, but it's showing that there's 2 numbers involved. The first number here on the left, and then the right number, second number on the right. And we see those numbers increasing from 1 to 2 to 3 to 4 on both sides of the center point. And the difference between them starts off with 2, and then 4, 6, 8, and so on. So this is a totally different process than we're used to. It's 2 one-dimensional scalar numbers in 3 dimensions. Now, we're going to see that there are in 3 dimensions, there are 3 of these going on, orthogonal to one another. Here I'm showing 3. It was too hard. I mean, 2. It was too hard to show 3. But you can see that you've got 2 numbers in each one of them. And then if the z-axis were shown, you'd have 2 more numbers for a total of 6 one-dimensional numbers. So the idea here is getting into a realm of things that we haven't noticed or we haven't encountered before. But notice also that there's no fixed coordinate here. We're not talking in terms of anything but the expansion of a number, a scalar number, and it's going up in value from 2 to 4 to 6 to 8, just as a line would if it were growing. So the length of the 1D line increases in both directions out. So we would say that that direction is out as opposed to another direction that would be in. See, that's why we put the word in quotes in terms of the way we're talking about it. It's not the same as the direction defined by Pythagorean's theorem on the unit circle as he was showing, like as if it were different points in the compass rose. The length of the 1D line increases in both directions out from the middle point. It's not moving. So there's no concept of an x position or location needed, and only the magnitude of the length of the line at a given point in time, which is just a sequence of numbers and highly predictable. We've seen how scalar numbers with 2 reciprocal aspects called rational numbers perfectly represent 3 fundamental magnitudes coming out of the first fundamental postulate of the RST. The first magnitude is unit scalar motion, taking the form of space over time, which is velocity and normal change of position motion. But here it's an increase of space and an increase of time, 1 over 1, which can be plotted graphically by plotting increasing time along the vertical axis and increasing space along the horizontal axis of n by n grid of orthogonal values, as we are going to show next. In this graph, the value of progression, P, the progression of space and time, consisting of increasing space and increasing time, or 1 unit of space for each unit of time, proceeds uniformly along the black diagonal line here with the arrows. And it proceeds uniformly along that line. See, is this as 1 unit of space increases and 1 unit of time increases, then we get, by Pythagorean's theory, right, the hypotenuse of the right triangle there. And then the next unit goes up, and of space goes up, and then this unit of time increases, and because they're orthogonal, the thing just continues to move like this. That line of progression, it moves uniformly along that diagonal line as P is equal first to 1 over 1, and then 2 over 2, and then 3 over 3, and clear up ad infinitum to whatever number, n over n, and infinitely, it never stops. So the magnitude of the space-time ratio there is always equal to 1, because st equal to n over n, any number over the same number is always going to be equal to 1. So in our RST-based theory, this unit magnitude, as we call it, is equal to the speed of light, designated by the letter c, and it's called the natural progression of the RST. Now, as I explained already, the only possible deviation from this unit magnitude of uniform scalar motion will occur if and only if a periodic reversal of direction is introduced in one aspect or another of the unit motion. When this direction reversal occurs in the space aspect, the continuous increase of the space aspect of the unit motion at a given point in time is replaced by a continuous oscillation over 1 unit of space. And from then on, only the time aspect of the motion continues to increase uniformly. That's shown here, see? At this point, instead of going up to the next unit, we get a reversal in the space. This is the axis of space progression here. And so as time progresses upwards and space now is decreasing, then we get the green diagonal here, and then the space oscillates and begins to increase again, and time though continues on. So now we get this diagonal, and so on as it oscillates back and forth. Same way with the time oscillation. There's a reversal of the time as it decreases here, shown by the red arrow, which then, as space is increasing, causes this diagonal to go from corner to corner. Now there's a reversal again, and the time increases, and as space increases, that causes this diagonal, and so on as we get this oscillation. Now you have to think of this in 3 dimensions, not as a point moving along, but as an increase and decrease in 3 dimensions, which is inflating to a ball and then contracting to a point. So anyway, we see that in this case, the magnitude of the progression ratio is reduced from S over T, in this case here, to 1 over 2, from S over T equal to 1 over 1 to S over T equal to 1 over 2, and then 2 over 4, and then 3 over 6, and so on up to n over 2n. And same thing here. For the time, S over T, now we get 2 units of space for every 1 unit of time, then 4 units of space for every 2 units of time, and so on to 2n over n ad infinitum. So the reciprocal result then is equal to, except that it's reciprocal to the same result that we see in the space oscillation. Well, in this case then, the magnitude of the natural progression ratio is actually increased. 2 over 1, 4 over 2. You know, it's the same value of 2 over 1, no matter which point in space it's examined, we might say. It's still the fact that the ratio of these things is 2 over 2 here, and in this case it's 1 over 2. So this is a unit below this line, and this is a unit above it. So it's still a change of space and a change of time, but we have the values changing. Now people are going to say, well, things can't go faster than light. We're going to talk about that a little bit in a minute here. But in both cases, the deviation from unit magnitude is easily plotted on this chart. You can see here, it's just a chart that's showing changing directions of the oscillation using red vertical arrows. You can see those here in the case of the space oscillation, and then you see them here in the case of the time oscillation, as we've already explained. So the green diagonal areas going this way in the case of the time oscillation, and that way in the case of the space oscillation, progress uniformly in time or space. Okay, so once again, it's important to note that the plots of these three magnitudes of motion, s over t equal to 1 over 2 here, and for the space oscillation, and then s t equal to 1 over 1 for the natural progression, and then s over t equal to 2 over 1 for the time oscillation, are just plots of magnitude only. There's no vectors involved here. We're just plotting changes of magnitude. And so as such, they are completely independent of any fixed coordinate reference system. And that's really important to understand. In this natural reference system, as we call it, as it's referred to in the writings of Larson, the progression of the oscillating units, that is the time progression of the space units and the space progression of the time units, is mutually orthogonal due to the fact that the first fundamental postulate posits that time and space are reciprocal aspects of the of motion, of the natural progression. So, you know, there's no arguing, there's no making this up. It's just a fact that comes from the what we deduce from the postulates. The reciprocity of these two aspects of the natural progression is captured by the orthogonal plots of their respective oscillating magnitudes. Representing the reciprocity of the two aspects as orthogonal progressions also demonstrates that there is a possibility that the orthogonally progressing entities may collide at some future point in time. There may be one up here in the future of this one that's progressing in time only, oscillating and progressing in time. There may be one up here like this that's progressing along the increase of space, and so they could collide at some future point in space and time. We can see this in the next chart here, the next slide. See, you can see, oops, excuse me. You can see that here we've got, now I'm going to have to explain what these mean, but this is an oscillating space unit that is going like this, designated as the space unit displacement ratio, Suter. And it's progressing in time because this is the direction of time progression. So it's increasing in time, but the and its motion equation is st over equals 1 over 2, remember, and it's progressing vertically then with time, while the time unit displacement ratio, or Tudor here, where it has an st equation of st equals 2 over 1, progresses horizontally with space going in this direction, the space progression. So you see the likelihood that they could meet at some point in space and in some point in time. And if they do, then the possibility of them combining present, and it's depicted here by the plot in the this plot here in the upper left-hand portion of the chart, where the space progression of a tutor incoming this way and a time progression of a suitor brings them into contact and they combine, and the result is this this, what's that, magenta colored line, where now, you remember from our black line in the previous slide, this diagonal line in this way is the speed of light. So here, where they were progressing in time and space, and at some at the rate of the progression of space and time, here now they combine together, and their two progressions, rather than being, I don't want to say eliminated, but that's really what it was. If you look back at this progression here, when these reversals take place, it really just stops the progression along this diagonal line and changes it into this vertical line. So this progression stops immediately when those vibrations take place. So here we have this magenta combination, and we identify that with a photon because it's traveling at the speed of light. In the theory development of the LRC, we designate it as an S pipe T unit, as shown in the chart here. This stands for suitor and tutor combination, and the use of the pipe symbol in the middle differentiates the equation from the combination of these oscillating units from their equation of motion. The equation of motion is space over time in a mathematical sense, so we had to use another symbol. So in this way, the fact that the suitor and the tutor are reciprocal entities within the combination is maintained, but without confusing us with the combination of their equation, their scalar motion equation in terms of magnitude or speed. So I hope that makes sense. S pipe T, capital S pipe capital T, is indicating two reciprocal entities, suitor and tutor, combining together, and their resultant progression then is at speed of c along that same line as our previous chart. The other two plots here now plot two more possibilities that arise once this ST combination is formed, where the lower one, this one here, you see, shows a collision between an initial ST unit and with a second suitor. So here comes the ST along this way, but then a suitor progressing along the timeline collides with it and alters it, lowering its speed towards the blue, not the blue, the red, towards the red. So we've got a little more red in this direction. And then the opposite thing happens here as the ST unit's going along the line and the incoming tutor collides with it, combining with it, would make it actually go faster. This would be the 1-for-1. This would be something more than 1-for-1. And this would be something less than 1-for-1 speed because of the imbalance in the amount of space and time in the combination. So notice that the progression of this new suitor-tutor combination then deviates from the unit progression of the initial combination when there was a 1-for-1 ratio between suitors and tutors. Now, on this basis, we can easily understand that there are three possible ST combinations, and only three. One where it's unbalanced to the time side, and one where it's unbalanced to this to the space side, or we might say unbalanced to the suitor side. It has more suitors than tutors, and this one here where it's unbalanced towards more tutors than suitors. See, so here they're balanced, here they're unbalanced to the space side, here they're unbalanced to the time side. So when the numbers equal, the magnitude of the space and time progression of the combo is the unit magnitude, or the speed of light, where st is equal to 1/1, and we've designated that as c. I ought to put that in there. I should have, but we can call it here c, if I can draw with this. And then this one would be greater than c, so we could maybe indicate it with a plus c, or c plus we could have. And this one with a negative c, where it's less than the speed of c. So if the initial st unit collides with an incoming suitor, the magnitude of the combo's progression is lowered below the unit value c, indicated by a shift in the combo space and time progression plot more towards the orthogonal time progression, and thus indicated by a more red color here, and then this one by a more blue color when there's more tutors. Well, with this much understood, then there are two crucial observations that should be noted, among others actually. But first, up to this point, there's no such thing as matter in our theoretical development. We are strictly dealing with the logical implications of the first fundamental postulate of the RST, which happily has led us to three combinations of progressing space and time as entities of nothing but motion and combinations of motion. Then the second fact that is crucial to note is that the magnitudes of the motion combos here include units with values both above and below unit motion, which we have identified with the observed space and time magnitude of light, designating it as c mathematically. So in the theory of the LST community, physical entities with speeds above the value of c are called tachyons, and those with speeds below the value of c are called bradyons, and those moving at the speed of c are called luxons. But normally, when tachyons appear in an LST theory, it's usually cause for rejection of the theory altogether, because it's seen as something violating the known laws of physics, LST physics. However, as we've seen in our plots of magnitudes of space and time progressions, the tutor and ST combos with more tutor than suitor magnitudes are simply logical deductions from the fundamental assumption of the system. And even though they must exist in the new system, it's important to recognize that they are not particles, quote unquote, of matter. Therefore, they're not part of the LST, which is based on the assumption that the number of observed particles and their fundamental interactions constitute the program of research for that system of theory. Our new system of theory, on the other hand, in it, those assumptions don't hold. And so the laws that have been discovered in that system exist only in the appropriate realm of that system. In other words, while the new system will inevitably incorporate the laws of the legacy system to some extent, once particles of matter emerge from the theory, because these laws come from observations, after all, especially the standard model. But before that point that they emerge in the theory and from our logical development, it makes no sense to conclude that those laws would apply. All right, so at this point in the presentation, we need to talk about mathematically now formulating the suitors and the tutors and their combinations as ST combos. So, so far we have the three space-time ratios of ST equals 1/1, and then we have 1/2 and 2/1. We can immediately recognize these three integers, these three integer ratios, as belonging to the group of rational numbers, which is written here in this form here. It's the middle here, is where would we consider the origin, where it grows in both directions, the positive direction and the negative direction. But they're inverse. 1/1 would be the origin of our unit progression in the natural system. But this is, of course, not something that is unique to our system. This comes from the mathematicians, who call it a group because it has several characteristics. One, it has an identity number, which would be this one here, that any other member of the group is multiplied by it. It doesn't change it. And then also that every member of the group has an inverse. So we see 2/1 here is inverse to 1/2 and vice versa. And inverse, or 3/1, the value 3/1 is inverse to this member of the set here, 1/3, and so on ad infinitum. So it has at least those two properties of the group, and there are others as well. Well, this is important to understand because it's the mathematics. Oh man, I can't get used to how to operate this slide with the mouse. The second fundamental postulate of the RST now becomes important to understand, because it says that the physical universe that we just talked about, that consists of nothing but motion in discrete units and in 3 dimensions, with 2 reciprocal aspects, space and time, conforms to the relation of ordinary commutative mathematics. Its magnitudes are absolute and its geometry is Euclidean. Now, that's really a contentious point with a lot of people who have been following Larson. A lot of them wanted to do away with it, actually, or modify it substantially, because they couldn't see how that could possibly lead to anything, given relativity, and given, which depends on relative values, and given quantum mechanics, which depends on non-commutative mathematics. So many students of Larson's work and the RST find it very difficult to accept this postulate in its present form. They take issue with the restriction to Euclidean geometry too. But of course, observations have shown that the universe actually does conform to Euclidean geometry, that it's as flat as a pancake, as they say, and it doesn't have these non-flat geometries that modern scientists have come up with. They take issue also with the restriction to absolute magnitudes, and they take issue, as I said, with the restriction to relations of ordinary commutative mathematics, which are absolutely essential in the quantum mechanics. Now, again, I should make clear that this assumption, like the first one that we're talking about, applies to the development of the theoretical universe of the RST. We seek to develop the logical implications of the 2 fundamental postulates, and then we look to see how these compare to physical observations. We must not succumb to the conclusion that the laws of the legacy system of theory, such as those governing Newtonian physics, the LST, including quantum physics and the theories of relativity, and their associated mathematics and geometry, will not or cannot eventually emerge from the theoretical development of the new system of theory. In other words, it's not that we're not going to be able to explain the things that are observed in quantum mechanics in the context of the new system, or be able to explain those things that are observed in special and general relativity in terms of the new system. It just means at this point, it's premature to rule it out on that basis. As we saw in last week's program, leading theoretical physicists of the LST community, like David Gross, fully expect a revolution to come in our understanding of the nature of space and time, which will enable us to break through the current impasse that plagues these guys. Knowing that there is no greater revolution in our understanding of the nature of space and time than that inherent in the RST, we should not ever give up on it prematurely because of perceived conflicts with the LST that has led society down the dead-end road to this enigmatic theoretical development. So proceeding on this basis, then, we see that it is expedient that we study scalar numbers to see how we can use them to formulate the motion, combinations of motions, and relations between all these in a manner that is consistent with the two fundamental postulates of the RST. It's important to understand this because scalar values are values of magnitude only. They have no direction in space or time, as do what have come to be known as vectors, even though these new scalar magnitudes have what we call direction, which we put in quotes, because we mean it in the sense of opposing polarities. We've got a direction that's outward in one sense from the center, and another direction that's outward from that same point in the opposite direction. So we need to understand that's not, due north or south or east or west on a fixed grid system. That's just a matter of whether it's increasing or decreasing in one of these two directions. So we mean this in the sense of opposing polarities rather than in a sense of a fixed reference or coordinate system. So not only that, but we recognize the fact that there are exactly two of these opposing directions or polarities in each physical dimension. So there are two directions we call left and right, up and down, back and forth. But these are the two polarities that constitute each of three orthogonal dimensions of Euclidean geometry. So when two or more of these single dimensions of geometry are oriented orthogonally as different dimensions and taken together, entities of higher dimensionality are formed, such as the 2D plane or the 3D cube. However, it's important to recognize that there is a serious disconnect between the magnitudes of 1D lines, 2D planes, and 3D cubes, those figures of geometry, and the scalar numbers used to formulate them. We can use two scalar numbers to calculate distances between 0D points and call it a 1D line, and we can do the same thing in two orthogonal dimensions and call it an area, or even do it in three orthogonal dimensions and call it a volume. However, the scalar numbers x squared, x to the second power, or x to the third power, or x times y, or x times y times z, do not correspond to all physical magnitudes of lines, areas, and volumes. And this was a huge problem up until the end of the 19th century, when the existence of so-called real numbers were logically deduced as lying in between the integers of our scalar number line of rational numbers. Together with the invention of the imaginary number, the advent of these real non-integer numbers marked a tremendous advance in the field of mathematics, particularly for what is now known as vector algebra, which enabled physicists to advance the LST theory in terms of particles and the forces acting on them with magnitudes and directions represented and calculated in a fixed reference system. However, in the RST, at least to this point in the theoretical development, we're restricted by the postulates to magnitudes of scalar motion in discrete units, formulated with scalar numbers. Now, in this next slide, we see the rational numbers that we are using and have ruled out the real numbers. So we're dealing only with these. We don't have any of the irrational numbers, they're called, in our system here, see? But we're using what are called what is called an interpretation of the operation of this thing here, where normally you could interpret it as 1 divided by 2 or 0.5, 1 divided by 3 or 0.3333, so on. But we're not interpreting it that way. We're interpreting it as an operational number where it's a relation between these two numbers that's important. They're analogous to the scalar numbers of the 3D fixed coordinate system, which is measured in scalar numbers running in two directions of each dimension, as I mentioned, positive and negative, beginning with 0 though. And I say it's analogous because to obtain these magnitudes, we simply take the difference between the two reciprocal aspects of the rational numbers. So that you see down here, 1 minus 1 for this number here would be 0. 1 minus 1 is 0. 1 minus 2 is minus 1 for the corresponding number here, corresponds to this one. 1 minus 2 is equal to minus 1. And then over here, 2 minus 1 is equal to positive 1. So you see, it depends on the operational interpretation. When operationally interpreted numbers become reciprocals, where the difference between their reciprocal aspects is analogous to the corresponding scalar integers of the fixed coordinate system, we end up with the fixed coordinate system numbers that we're familiar with. So these, I think these are, I don't think these are a group, you see, because you can't multiply any member of the set of the group with the identity number, which is this one right here, and come up with the same number unchanged. So because 0 times 1 is 0, 0 times any member is 0, not itself. So this is really not a group, and we can see that it's actually derived from the real group that is the rational numbers. Well, when these are listed along the x-axis of a 2D fixed coordinate system, an imaginary number allows them to also be listed along the y-axis, then the two magnitudes define a location in a plane, as we saw in the video. Similarly, a third application of these numbers, designating the divisions of the z-axis in a 3D coordinate system. The three magnitudes then define a location in a volume. However, the algebraic manipulation of these numbers as locations in a plane or in a volume is not as straightforward as one would hope, and the whole of the 20th century and a fair portion of the 21st century already has been spent studying and researching the solutions to that challenge. But without going into the details of the matter, we can say that the biggest problem that faces the LST system of theory is that quantum physics requires this fixed coordinate system with these numbers starting with 0 at the origin as a background. It can't do quantum mechanics, quantum physics without it. But on the other hand, general relativity is incompatible with a fixed background coordinate system. So the two just are at odds, and they can't bring them together as one unified theory. Well, the good news, at least for us, is that out of the natural non-fixed background of scalar motion, which we've seen, the natural progression, comes the elementary particles of the standard model of particle physics, as we'll see in this next slide here. And we see these and no others are formed from the logical combination of ST units, as shown in this slide here. We see all the fermion combos right here. There are two chiralities, a left-hand and a right-hand side to them, just as is observed in nature. And that we also see that it consists of all the stable quarks, and then the leptons, like the electrons and neutrinos, with the exception of the Higgs boson, which we still believe is dubious. But all these are part of the standard model of particle physics, which has been built from collisions and observing how nature behaves. So this is amazing. We just take our combinations of ST units and these particles come out. They are made up of combinations of ST units. And some are balanced, as we'll see in a minute, and some are unbalanced, and they just show up just as expected, just as observed, which is just something amazing. And the bosons as well. We will explain how all this works, but we've got the photons, and then we've got the W plus and minus bosons, and even the Z boson, just as LST does. And it's just amazing how those came out. For instance, the electron has a negative charge right here, opposite the positron's positive charge right here. And when the up and down quarks, here's an up quark and here's a down quark, and you get a couple of up quarks and a down quark, and then you get a couple of down quarks and an up quark, and so on to form higher combinations, and they all come out with these numbers that we've got in terms of suitors and tutors in the unbalanced ones and in the balanced ones. And this is just amazing, and it's just simply cannot be attributed to coincidence. But even then, that's not all. When the protons, neutrons, and electrons are combined, they actually form the elements of the periodic table, as shown in this next slide here. See, here it is the ST combo consisting of an electron. This is just, not shown as in our schematic. We build it, but for simplicity, it's shown this way. But it's got this charge, this -3, an imbalance of red towards the suitor. So we see that. But in the meantime, the proton, when we combine the two up quarks with a down quark, or whatever it is, I can't remember, I always get them mixed up, we see that the difference between those charges is +3. 2 plus 2 is 4, plus minus 1 is +3, and that the electron then would fit right in there and neutralize it, if you will. Then when we add the neutron in, and it has 1 up quark and 2 down quarks, if I've got it right, and the difference between that, -1 plus -1 is -2, and then +2 is no charge at all. So we add those across here, -1 and 2 gives us a +1 in the atom, and this 2 here added to that -1 is +1, and that 2 added to this one is a +1. So we have 1, 1, 1, +3, and the electron is a -3, and voila, the deuterium atom then, the first atom to be formed with a proton, a neutron, and an electron, come out perfect. As far as the balance of suitors and tutors are concerned, they're all balanced out, and we don't have what is normally called a charge, which we know in a universe of motion actually has to be a quantity of motion. All right, but then that's not all. Look here. We can combine then a proton, you see here, this is the proton, and then 2 neutrons, this is the neutron, 2 of those, and those charges then come out just exactly what they ought to come out, with the 1 electron here and 2 electrons here, and then they're completely balanced. And that's just what the configuration is of tritium and helium-3. It's just amazing. So I know I'm just kind of hand waving this stuff through. It's just a schematic representation, but we don't have time to get into the details, but those details are on our website, and we'll get into them eventually in this series of articles or lectures on YouTube. But we can see how these things balance out. Well, when we consider that all this remarkable correlation with observed properties of the standard model particles necessarily falls out of the fundamental postulates of the reciprocal system, then one has to pause and give the work of Larson serious consideration. But then this is not all. These combos can continue to be combined to form elements of matter as we go up the periodic table. So there's a whole lot more to say about this, of course, but it should be clear from this much that we need a mathematical formulation of the ST units and the combos that follow from them, which will enable us to manipulate and calculate all their properties, not just the 1D electrical charge properties. See, we haven't said anything about magnetic properties. We haven't said anything about mass properties and so on. But as far as electrical charges are concerned, it works out beautifully. So we've got a lot to do. But one of the most touted achievements of the LST community is their ability to use quantum physics and the Schrodinger equation and so on to calculate the value of what is called the anomalous magnetic moment of the electron to a very, very high precision. And this is what gives them such confidence in the quantum physics. But we need a mathematical formulation of the RST-based theory, which will likewise enable us to do similar calculations for scalar magnitudes that include this atomic spectra, for instance, and these values of the anomalous magnetic moment and the mass differences between the proton and an electron and so on. In our plan to do this, we begin by assuming that there should be a one-to-one correspondence of the Euclidean geometry and the mathematics of the RST in terms of dimension, magnitude, and direction, quote, again, the special use of direction as in polarity. We have found that such a correspondence does indeed exist, as shown in the Tetraktys, the Greek Tetraktys on the one hand, and what we call Larsons Q on the other hand. Moreover, and more to the point actually, we are also uncovering an amazing correspondence of both of these fields with the field of physics, where the concept of scalar motion clarifies the meaning of energy, mass, force, and acceleration. Now, that's amazing. And it does it in terms of a new multidimensional scalar number system, which we are developing. However, we're going to have to leave the details of that to be discussed in part 2 of this lecture next time. For now, it'll suffice to explain how the logic of the ST units and their combination is represented schematically in these diagrams. So here we have if I keep moving the mouse without first changing the focus, it messes up. But this is our explanation here, as we've already been explaining. ST units are a combination of 3D oscillations as shown on this slide. See, I don't know how this will work. I could just, yeah, so you can see it there. The 3D oscillation. I should have been able to show how the blue goes down to a point in the red, but I wasn't able to do that. I could only show how the red collapses to a point as the blue expands to full. But this is the oscillation that we're talking about, and it is used systematically in the following way. Oh gosh, can't get used to changing the focus first. So one oscillation is the space oscillation, which is oscillating as space over time, and the other is the time oscillation, which is oscillating as time over space. So schematically, we represent the suitor, which is the space oscillation, with the color red, and the tutor with the color blue. As an ST unit with one suitor and one tutor is represented by two dots down here. See, now we're talking. One red on the left. So let's take this one, for instance. Here we have this red dot here on the left, and then another one, the blue on the other end of this line is a tutor, representing a tutor. So the red is a suitor and the blue is a tutor. And if this middle dot along between them is green, it means that their number, whatever it is equal. We've got the same number of suitors as tutors. And so this is what the green here indicates. But if there happen to be more suitors than tutors, more red suitors than blue tutors, then in the middle we indicate that imbalance towards the suitor side with a red dot in the middle. And if it's the other way, with more tutors than suitors, then we represent that with that middle dot being a blue dot, meaning it's unbalanced towards the blue side or the tutor side. So there's more time involved in this one and more space involved in this one, which means, of course, its propagation is less than the speed of light, and this one is more than the speed of light. But this one, where it's green, is balanced, so its propagation is the speed of light. So we call that the photon. But we can combine three of these in different ways, and they become bosons, because you see here, if we combine three of the balanced ones together, you can see how they fit. We can combine it, because like stacks of wood that are parallel to one another, we could combine as many as we want, but we start with this three, and you'll see why here in a moment. But we could also combine three of the other boson, or into bosons, three of these ST units that are all alike into this unit here, this boson, which we designate, and I forgot to write it down, but it would be the W minus boson, and this one would be the W plus boson, and then this one would be the photon. So that's how we would combine those into bosons. But now if something happened and they ended up being reconfigured so they were connected end to end, forming a triangle like this, then they become fermion combos. It's the same thing, but just configured differently. And when that happens, these three then become the electron with these three unbalanced units here, and which will match the three unbalanced, but in the opposite direction of the positron. It's positive. So that's amazing. If this is all considered, these three imbalances are considered as one charge, then as one, it would be called a charge, and people don't understand what a charge is. Then we can see how they're exactly opposite. And then, as we saw before, they fit magically into the other combinations of fermions, the quark combination making up a proton, and the quark combinations making up a neutron, and so on. And they all fit together just perfectly. So something is amazing here. And then we see the neutrino in the middle, and it's made up of these balanced photons here. And as we're going to see later on, you could add photons, these photons, to these charges here, changing the absolute values but not the ratios. So we could see that electrons could go up to higher and higher energies without changing the charge. So that's amazing. But anyway, I think that will give you an idea of how we how these combinations actually work. And they all come out. It's very easy to see. Anybody that wants to look into it can see we haven't cheated, we haven't fudged. It just comes out of the fundamental postulates of the system. So now the minimum numbers then are ST equals 1 over 1, 1 over 2, or 2 over 1, as shown here on the slide. And combining these in the way that we've explained produces these combinations. Now, what's really interesting also is that since the boson combos consist of parallel units here, I think I've already mentioned this, they are easily combined with others. It's just like stacks of wood. I mean, a bundle of sticks, right? I mean, it'd be easy to combine more sticks or pile more into that bundle. But the fermions, on the other hand, if you take sticks and put them end to end and forming a triangle, how do you fit another triangle on that? It's not so easy. And this is the same thing that's observed in the lab, that these bosons are easily combined, but not fermions. So again, this is a well-known property of these two types of entities. That how could this be a coincidence? It's just incredible to think that these logical combinations that are just a number balance or a combination of suitors and tutors constitute these things that bring out these electrical and fermionic properties that you wouldn't have been able to do this in a million years if there wasn't something to this. So but see, the problem is now with the math, these are simple numbers. They're just counting how many, these could go up. We could have 2 and 4. We could have, or we could have 2 and 3. We can have 4 and 5. We could have any combination, right, where there's one difference, or we could have maybe 1 and 5. Who knows, so that there's a difference of 4 between it. This is really unbalanced. Probably not very likely that could happen, but the possibility is there. But this is all the mathematics can do, and yet these things have 2-dimensional properties and they have 3-dimensional properties. Like mass, 2-dimensional is like magnetism. You can't find them. People think they're searching for a magnetic monopole, but that's a 2D plane. You can't have a 2D plane that only has one side. It's impossible, and but you can have a line with 2 different ends. So we have positive and negative ends of a line, or in this ST combination, but when you have a plane, you've got to have both sides at once, which is what magnetism is. There's no monopole. For every side, there's always going to be an equal and opposite pole, if you will. And no matter how finely you divide it, you're not going to find it to be otherwise. Just like you wouldn't find a plane that only had one side. So it's very easy to understand, but our math doesn't show any of this. We can't find these characteristics, 2-dimensional and 3-dimensional characteristics from this kind of mathematics. It just use these units of 1, 2, 3, 4, and so on, the natural numbers. We clearly need a more expansive and comprehensive mathematics to do this. So in next week's lecture, we'll examine the developments that we're so excited about, that have where we've made progress in this regard. But in the meantime, please share this video and be sure and subscribe to the LRC Physics channel. Until next week then, have a good night.